Hello, in this modern OpenGL programming video, we're going to be looking at basic lighting because up till now, if you look at the result from our previous video, which was just covering colors, let this load. What we've got is this cube and we've got a light source. At the moment, the entire color just looks uniform. It almost doesn't look like a cube. It almost just looks like, well, a six-sided shape, and I'm pretty sure, and I'm positive, if we get the right angle, we should be able to almost make it look like an equilateral six-sided shape, which is, well, called a hexagon. But you can see what I mean. It doesn't look, the lighting doesn't look very realistic, because realistically, if for example this is the light source, which it is, this corner here should be brighter than this corner here. This side here really should be very dark, because if there's only this light source and nothing emitting light from behind it, why would this be light at all or be this bright? So in this basic lighting video, we'll cover improving the lighting system so we can have a more realistic effect. So what you want to do is go to your lighting vertex shader. The lamp shader we're not going to be changing, because the actual light that's being emitted, we're happy with that, because essentially what we're doing is changing the way our object almost perceives light, the way its surfaces are, and that will make the object look different. The actual light being emitted to it is still going to be the same. So if we go to our lighting vertex shader, this doesn't require many changes. The first one is I need to zoom in first so you can see a little better. Zoom a bit more. Yeah, fine. So first of all, what you want to do is add a layout, and this is going to have a location of 1. Location equals 1. And this is going to come in, and this is going to be a vector free, and this is going to be normal. It's not going to be normal, it's going to be a normal vector. I'll explain what a normal is in a second. Let me just quickly write out this code. Obviously you'll copy it as well, and then I'll show you what a normal is, and I'll explain that. Out vec free, so you'll be going out will be a normal, and then the fragment position, so out vec free will need the frag position. As usual, these videos are based on the work from learnopengl.com and open.gl. For more information about everything that we're doing, to see great screenshots and great images accompanying what we're learning, feel free to check out those links. There'll be links in the description. Feel free to check out those websites. There'll be links in the description, and they're fantastic for learning. They're a great way of improving the knowledge that you'll gain from this video. The other thing I want to mention, as with pretty much with every other video in this series, even though we're using GLFW and we're on Xcode and we're on a Mac, you can do this on Windows, do this on Visual Studio. You might need to change a few things from GLFW to a different framework, but the tutorial will work. So my particular setup is independent of the actual code that we're writing. So the model view projection, we're still going to be using that. That's very important. So for this, we got projection view model. We're not changing that at all. Then we need to do frag position, which is what is going now. Frag pos equals vec free. And this is going to be model times by a vec4, which we're going to create from the actual position itself. So position, which is, we already had it right here, so that's nothing new. Position, and we're just going to put the final value as 1.04. No, 1.0, not 4, sorry. Normal is going to be a 3x3 matrix, so map 3. It's going to be transpose inverse model, and what we're going to do is times that by the normal. Again, feel free to check out the links to see. They've got a bunch of description of what each one of these, just each little line of code does. Obviously, I'll be explaining it as an overview of what our project is doing. So before I continue and do the fragment shader, let me save this. I've opened some images off Google to demonstrate or illustrate what normals are. So normals are basically a direction that is perpendicular to a particular surface. So as you can see, this is 90 degrees to this particular, each one of these surfaces. And what this is used for is when calculating, well, lighting, because it determines the way lighting bounces off it, the way it reacts to it, and as a result, it looks a certain way. A powerful technique is to change the direction of the normals, which you can do. We'll be covering that as well, don't worry, in this series. And that allows you to change the way the lighting reacts to it, which makes the object look different. And what you can even do is have, let's say, a flat object or a relatively flat object with very little polygon, with a very little polygon count, and by changing the normals, we can add the illusion of depth. That's the reason when you play a game sometimes and you see some sort of object, especially when it's on a wall and it's relatively flat, but it looks like it has a bit of depth to it, and you're quite far away from it, and it looks like it's got depth. When you go close, and especially when you look at it at an angle, it doesn't have depth anymore, or very little depth, and that's, well, that is the limitation of this system. Obviously, if you want to get around that, you need to use some sort of tessellation technique, which actually has real geometry. That's obviously a lot more expensive in terms of processing power. This is a lot cheaper in terms of processing power, so this is really preferred in the gaming industry, simply because you're not just drawing one sort of simple shape, you're drawing a whole heap of polygons, which this technique will allow you to reserve some processing power. So here's another image to show it, and well, obviously this is a bit more complex, but the principle is exactly the same. So now that we've done this, if we go to the lighting fragment shader, I'm going to zoom in. I'm going to add a bunch of new lines. And the reason I'm doing this is just so I can easily scroll up and down for this video. So what we're going to be doing is, after this color, we are going to do in vec3, and it's going to be those frag positions that we were sending out from the Vertex shader. Going to be in vec3 normal, and for the uniform vec3, we need the light color and we need the object color. What we also need is a vector for the light position, because we are factoring the light position, because the lighting will vary depending on what part of the surface you're looking at. We need a vector 3 for the view position, because obviously that is important, obviously, as well. View, pause, and now if you go to your main in here, we'll deal with this color. Actually, you know what? This color is going to change, so I'm going to get rid of all of this. There's 3 types of lighting techniques that we'll be using. The shading techniques, there'll be ambient, diffuse, and specular. First one, which is ambient lighting, is just like the general lighting that's in, let's say, a scene. So you can, I don't want to say it's almost like the light from the sun, but it's just that general light that's just always bouncing around the room, that's just generally there. It doesn't have a particular, like, what's it called, origin, a position. It doesn't have anything like that, or direction. It's just there. So that allows it to provide some, basic sort of color, some basic property to your object. Then on top of that, you add diffuse lighting and specular lighting to make the object a unique and, well, interesting object, to make it look more like what it would in the real world. But we need some ambient lighting, which is, like I said, just the general light that is applied to it. So this is float ambient strength. I'm going to put a value of 0.1. Feel free to change these values. I would recommend doing that. It's a great way of learning, see what happens, see the limitations of the variables as well, the bounds. Now I'm going to have a vector 3 for the ambient lighting. This is going to equal ambient strength times by the light color, which is from the previous video. And that's it for ambient. Now we're going to do diffuse lighting. Diffuse lighting, you can sort of think of the more sort of, it takes into account the direction and the normal. So it's essentially the lighting that you would, okay, what's the best way to put it? Okay, imagine a cube, like I was saying, the corner that's like the top of the top surface, the corner which is nearer to the light source, that will be brighter compared to the corner that is furthest away. That's essentially what diffuse lighting is. It adjusts for the actual position, like the angle as well is to do with the angle. So like if you were to have a light source at 90 degrees, that would emit more light than, let's say, one at 5 degrees and it was shinier. That's essentially what diffuse is. You don't generally just have ambient, diffuse, or specular lighting. You have all three and different intensities, different strengths, etc. And that allows you to create a realistic effect called combined lighting, and also very often called Phong shading. You might hear of that Phong, P-H-O-N-G. Definitely recommend Googling that and having a look into that a lot more, because very interesting stuff. So VEC3, this is going to have a normal. This is basically going to normalize our normal. So normalize the normal. I'm going to spell it correctly, obviously, first. And now we need the light direction. And this is also going to be normalized. And for this, you just put light, pause, and frag pause. You just basically get the difference between them, and that will tell you the direction in which the light is, well, pointing. Simple as that. Float diff, and this is going to be the difference between the normal and the light direction. So we're going to do max the dot product of norm and light direction 0.0 VEC3, and this is going to be diffuse equals diff, which is what we just created right here, times by the light color. We're always going to be factoring in the light color, because at the end of the day, if we have a white light shining on something, we don't want it to be blue or red. Well, it has to be what the light is. Obviously, it will vary depending on the actual material that is applied and the sort of properties of that object, but the actual light itself should be, well, the light color. So now that we've done the the diffuse lighting, we can go into specular, which is really cool. Specular lighting is the best way to put it. This is the way I was taught. Is imagine if you think about a sort of like a snooker ball or a pool ball, which has a sort of like little circle light shine on it. It's that little shiny light on a object, and you might think, oh, how many objects really have specular lighting? But I'm literally looking around my desk and I can see so many objects with some level of specular light. My monitor stand, my capacitive pen, which has some metal on it, has some specular, essentially what would be specular light on it. My keyboard has it. My phone has a bit on the corner. Like, there's so many objects that you wouldn't even think, because all the examples that you get when you like Google it and you learn about it are always those really shiny extreme examples, like a cue ball, like an 8-ball or something. But it's on so many objects in the real world. It's ridiculous. I've just seen another one, a piece of like this plastic. So it is useful, not just for something really shiny. So okay, let's get back to it. I was just sort of went off, I was getting really passionate. First of all, we need to do a specular strength, because like I was saying, there's different objects on my desk, different objects in the real world that have, sometimes they're really bright, really shiny, sometimes it's just very subtle, and we need to be able to manipulate that, because if we just have one intensity, we won't get realistic objects in our game engine, whatever we're creating. I'm going to set this to 0.5F. I'm going to put view free, no, I mean vec free, not view free, vec free view direction equals normalize, and this is going to be the view pos minus defrag pos, just getting a difference, very similar to what we did before with the light direction. And now we need to get the reflection direction as well, because this is very important for specular. Reflect direction equals reflect, and this is going to be a negative of the light direction, and it's going to take the norm, which is the normalized normal which we created up above in the diffuse section. We are going to do a float spec equals pow max dot, it's going to take the view direction, the reflect direction, it's going to take 0.0 and going to take 32. And what else we got left? We need to create a vector for the specular now, which we'll use in our calculation in a moment. So specular equals specular strength times by spec times by light color vec free result equals. Now all we need to do to calculate it is simply multiply everything that we do. I mean, need to add it up and then multiply it by the object color. So ambient, add up the ambient, add up the diffuse, add up the specular. I recommend trying to do that. Multiply them and just change things up, see what happens. You'll get some really interesting effects, and it'll be a great way for learning. So we're going to times that by the object color, which again we've already created. Object color, and finally we need to do color equals vec4. This is going to be the result, and it's going to have 1.0 at the end. So now we're all good with that. Now we just need to go to our main.cpp. In here, the first thing that we need to modify is this vertices array. The moment we have x, y, and z values for each one of those sort of, what's it called, the vertexes, sorry, sort of skipped my mind then what it was. And what we actually need is to also include the normal. So I've already got this created right here. I'll briefly go over it. Let me just paste it in. The normals are the same, but the actual 3 extra values on each one of the lines are the direction of our, I mean, the vertices are the same, sorry, I think I said normal, but the 3 extra values are the x, y, and z, aka the direction of the normals. The normal will stay the same for, well, every single, in this video, for every single face. And what I want you to try and do is try and figure out which face each one of these normals applies to and what is the direction once you've rendered it. Modify them, see what happens. That's going to be a great way of learning. That's always the best way to experiment. Change some of these values but keep some of them the same. See what happens. So once we've done that and you've got all that sorted, just need to change a few things when we're doing our VBO and our vertex array object. So if you go down to the position attribute, down here we're no longer doing 3 times because we got 6 different pieces of value on each row. We need to do 6 times, so that's all good. And before we actually do bind vertex array or actually unbind the vertex array object, we need to create a normal attribute. So normal attribute, we need to do GL. You know what, it'll be honestly quicker to copy and paste this. So what I'm going to do is copy and paste this. Let's see what we need to change. We need to increment this to 1, 1, 3, 6 is fine. And for this part, we need not do it times by 0. because obviously when it's free off, we need to do free times by size of GL float. Let me just scroll over a second so you can see what I've just done. That's essentially what I've done, but I've spelled it incorrectly. That's what happens when you do it off screen. Nope, that's definitely not it. Okay, that's all good now. See if I can get this positioned all nicely. Yeah, that would be good enough. So the normal attribute for the enabling, we need to use 1 for this. We are unbinding the vertex array object. Let's have a look. The lighting, that should not change apart from one little thing. Again, the position attribute is now going to be 6 times, but apart from that, we're all good. We're not touching the projection matrix at all. So if we keep scrolling down, we are using the lighting shader. We're using the object color location as well. But what we also need to do is do the lighting position location, assign that to our shader program, and the view position location. So I'm going to duplicate this a couple of times. So we got a light pause location. I need to change this to light pause. We need to change this to view pause, and we need to change this to view pause. So in terms of this, we also need to obviously update these as well. I'm just going to build this to make sure everything's all good. That's all good. It's still all working. That's just warning us that we haven't used it yet. The actual object color location will not change. The actual, what's it called, the light color location, I'm going to change that to 1.0f, but again, I'll recommend changing these values, see what happens. So what we need to do is create or pass in the value, the position for the light pause location. So we need to do GL uniform 3f, and you need to do light pause location, and for that we're going to do light pause .x, which is something that we created way up above a video ago. So we're going to do light pause .y. I think you can guess where this is going. Light pause .z. Now we need to do GL uniform 3f view pause location camera dot get position. My bad. What we've done, or what I did, was in the camera header, these are all private, but we don't have any sort of method to get the position, and I'll say we'll create them when we need to. So let's do that. So let me zoom in a bit more. You can definitely see that on a mobile device now. GL float get position, and this is simply going to return this position. Okay, so now that we've done that, if I go, oh sorry, this was a vec3, my bad indeed. Okay, that's all good. Now if we go back to the main CPP, I can actually use the position as a camera.get position, and for this you need to do get position.x. I'm going to copy and paste this. This will save some time, and change this to a Z, change this to a Y. The get view matrix, don't have a problem with that, we're leaving that as it is. For the model view and projection location, leaving that as it is. For passing the matrices to the shader, leaving that as it is. And in terms of the drawing of the box vertex array object, leaving that. The matrix 4x4 model, we are also leaving that, still drawing the same number of vertices, still drawing it as triangle, so we're also leaving that. And now we're going to be looking at the lamp shader, and realistically, if I remember correctly, yeah, this shouldn't need changing either. We should actually be ready to go now. Remember what it looked like. Unfortunately, I haven't run anymore, but I think you'll see a big difference when this runs. So we've got this surface. As you can see, like the top left side, like the top left corner, it looks a little brighter than the bottom left. And that's because that's where the light source is. And it's definitely evident on this side and on the top. Just look at the top compared to this side. Then look at this side. It's literally got hardly any light to it. It's a lot more realistic than it was before. 1 second. And as you can see, as I move across it, that is showing our beautiful dynamic shading. So what we're going to do now, because this is the end of the coding really for this video, I'm going to do a bit more coding technically, and all I'm going to do is go to the lighting fragment shader, change this specular strength to 2.0f, just modify this stuff up, and just to see, you can already see the sort of impact this has had. Look at that shine. That's the sort of shine that you get on like a cue ball on an 8-ball. Sorry, you can see it better on 8-ball than a cue ball. That is fantastic. Obviously, you don't get it on this side. You do get it on this side. That might be a little too extreme. So let's try 20 instead. Let's see how extreme this one is. Whoa. Obviously, when I'm looking at it from here, I can't see it, but when I'm looking at it from like this angle, damn, that is quite bright. I'm going to change this to 1, should be quite nice. What else can we really change? The ambient strength, let's change that to, I don't know, 10.0. Yeah, might be a little too much. 0.5f. Yeah, as you can see, this is obviously a lot brighter. This is almost looking more like a uniform color now, but it looks quite cool as well. But I'm going to change this back, and I'm going to leave this video here. What I want you to do is modify the values in here. In the vertex shader, honestly, there's not much that you'll probably be modifying. Modify the actual positioning of the object and the light itself. Modify, the positioning, which is here. Modify the actual color, location. Modify all of that really, really cool stuff. And just experiment with it. See what you can do. Actually, there was one thing I wanted to do. What was it? There was something I remember that at the start of this while loop, that was it. What I'm gonna do is every frame, like move the light position, so you can actually sort of see how the effect it has changes on our objects. So I'm gonna put light pause.x minus equals 0.01f, and I'm going to do the same for the Z position. Not going to modify the Y position because we sort of only want it to move along the horizon. You can make it move along the Y axis as well. That's perfectly fine. I recommend doing that. Try and make it circle around it. As you can see, we've got this sort of light, and as you can see, as it's getting further, the top side is like really dark now because it's at a really obscure angle. It's getting further and further away. But the angle for this is still not very obscure, so that is pretty darn cool. So yeah, I'd definitely recommend trying to move the light. If you can, this would be fantastic if we can get it rotating around the object itself. Here's another task. Add multiple lights. That will be awesome. Love to see your code. Love to see what you do. Thank you for watching. If you have any questions, feel free to post them on our education platform, sonarlearning.co.uk. There'll be a link in the description. Plus there'll be a link in the description accompanying that to our GitHub page, which has the source code from every video in this series. If you like the video, please give it a thumbs up, hit that subscribe button, and leave us a comment. And as usual, thank you for watching, and I hope you have a great day.